This part of the module covers bonding structure and properties. Here we're going to discuss the properties of metals, ionic structures, and both simple and giant covalent structures. Metals are what you'd find in the first three groups of the periodic table, including the large section in the middle. Groups 5, 6, and 7 are the non-metals, and we'll explore how these substances behave and bond to each other. Starting with metals, which includes elements such as sodium, magnesium, and gold. Properties of metals are that they're shiny, have high melting points, and are good conductors of both electricity and heat. We'll learn more about why later in the module. Metals are also dense. This means that they'll weigh a lot, even if you only have a small piece of them. Furthermore, metals are malleable, which means they can be bent or hammered into shape without shattering, and ductile, which means they can be drawn out into long wires. Mercury is the exception to some of these rules, as it has a low melting point, which makes it the only metal that is a liquid at room temperature. Next, nonmetals. These include elements such as nitrogen, oxygen, and chlorine. The properties of nonmetals are essentially the opposite to metals. They're dull, have low melting points, and poor conductivity. They also have low densities and they're brittle. Graphite is the exception here. It's a structure of carbon with a high boiling point and is a good conductor of electricity due to having delocalized electrons. Ionic structures are the bonding of metals and nonmetals. Sodium chloride, more commonly known as salt, is an example of this kind of bonding. Giant ionic structures form regular arrangements in repeated patterns to give 3D crystal structures. You can see here that in sodium chloride, each sodium atom is bonded to chlorine atoms in all directions, and the opposite is true for the chlorine atoms. Ionic forces are very strong, which means these structures have high melting and boiling points, since you'd have to provide a lot of energy to break them. These strong bonds mean that when solid, the ions in the structure are held together very firmly, so the structure cannot conduct electricity. However, when the structure is molten or dissolved in a liquid, the ions are free to move and carry the charge. This means that the compound can then conduct electricity. The ions present in ionic lattices have opposite charges. For example, in sodium chloride, the sodium ions have a 1+ charge, whilst the chlorine ions have a 1- charge. The bigger the charges on these ions, the stronger the bonds they form with each other, and hence the higher the melting and boiling points are. This can be seen clearly by comparing sodium chloride and magnesium oxide. In a sodium chloride, they have 1+ and 1- charges, and there is a boiling point of 801 degrees Celsius, whilst magnesium oxide with 2+ and 2- charges has a boiling point of 2852 degrees Celsius. Finally, we're going to explore covalent structures such as carbon dioxide and diamond. There are two kinds of covalent structures we're going to look at: simple covalent molecules and giant covalent lattices. Covalent bonds are when non-metals bond to each other. With simple covalent molecules, there'll be a few molecules held together by strong covalent bonds. However, the intermolecular forces between these molecules are very weak. These weak intermolecular forces mean that simple covalent structures have low melting and boiling points. Furthermore, simple covalent structures don't have free electrons or ions to carry charge, so cannot conduct electricity. Giant covalent structures are also non-metals, but they contain lots of atoms. They're arranged in regular lattices and are very strong due to having many strong covalent bonds. With these larger structures, you don't need to worry about weak intermolecular forces, which means they have very high melting points. Some giant covalent structures will conduct electricity if they have free electrons, but most will not. We'll explore this further when we look into allotropes of carbon.